For this week's lecture, we're going to look into open channels and their properties. In terms of the channel geometry, channel sections is referred to the cross-section of a channel taken normal to the direction of the flow. Hence, for a natural channel sections, they are generally very irregular and the shape can vary approximately parabola to an approximately trapezoidal shapes. While for artificial man-made channels, they are usually designed with sections of regular geometric shapes. For the purpose of stable channel design, the trapezoidal shape is the most commonly used channels for unlined earth banks. This table here shows the geometric elements for different types of section shapes. In this table, formula to calculate the area, the weighted perimeter, hydraulic radius, top width, hydraulic depth, and also section factors are given. This slide shows the commonly used geometric properties such as depth, stage, area, hydraulic radius, and so on. Depth here is defined as the vertical distance from the lowest point of a channel section to the water surface. Stage is also the vertical distance, but it is referred to an arbitrary datum. Area is the cross-sectional area of flow normal to the direction of the flow, while weighted perimeter is the length of line which is the interface between the fluid and the channel boundary. Hydraulic radius is defined as the ratio of the flow area to the weighted perimeter, or in other words, is R equal to A over P. Hydraulic depth is defined as the ratio of the flow area to the top width, while the section factor for critical flow computation, denoted as Z, is the product of the water's area and the square root of the hydraulic depth, or in other words, Z equal to A multiplied by the square root of D. While for uniform flow computation, the section factor is denoted as AR 2/3, which is the product of the water area and the 2/3 power of the hydraulic radius. This chart can be used to calculate the weighted perimeter, the cross-sectional area, and also the hydraulic radius for a circular shapes for the different flow depth. Let us look at this simple example. In this example, you are required to compute the hydraulic radius, hydraulic depth, and also the section factor for a trapezoidal channel as shown in the figure. The flow depth is 6 meter, and assuming that all the unit is in meter. So, using the formula from the previous table 2.1, the weighted perimeter, or P, is defined as the bottom width plus the line, the slanting line for the side wall. So in other words, P equal to 20 plus, because we have two side walls, so it's 2 multiplied by 6 square root of 5, since the given slope for the side wall is 1 to 2. That will give you the weighted perimeter as 46.8 meter. For the cross-sectional area A, again using the formula from table 2.1, A here will be equal to half, then the bottom width plus the top width, in this case is 20 plus 44, multiplied by the flow depth, which will get you 192 meters square. The hydraulic radius is A over P, so it's 192 divided by 46.8 will be equal to 4.1 meter. Then the D is actually equal to the A divided by the top width. It will give you 4.37 meter, and the Z is equal to 192 multiplied by square root of 4.37, which will give you 401 meter power 2.5. There's a typo error there. It's not fit. As for velocity distribution, the maximum velocity occurs near the free surface of the flow, while the minimum velocity occurs closer to the bank of the river or for man-made channel near the sidewall and also the bottom of the channel. This slide here shows the velocity distribution for various types of open channel shapes, and as you can see from this slide, the maximum velocity occurs just beneath the free water surface. This slide shows the velocity profile or the velocity distribution vertically in the flow depth. As can be seen in figure 1.2c, the velocity profile are distributed following a logarithmic manner. Even though, as we have seen in the previous slide, the maximum velocity occurs just below the free surface, to ease our calculation, we normally assume that the velocity are logarithmically distributed. For field observations, normally the velocity are measured at least 2 points, namely the velocity at the depth of 0.2 of the depth from the free surface and also at 0.8 of the depth from the free surface. Then both of these velocity can be used to calculate the mean velocity as shown in equation 1.1. Hence, if the mean velocity for the entire cross-sections is needed, equation 1.3 can be used to calculate this mean velocity, while equation 1.4 can be used to calculate the discharge passing these sections. So here, from here, Q is equal to VA. As for the kinetic energy, for an elemental area, dA, the flux of kinetic energy is equal to the mass over the time multiplied by the kinetic energy over the mass, while for a total area, the kinetic energy flux is as given in equation 1.5, which can be rearranged to get alpha, which is the kinetic energy correction factor, as given in equation 1.6 and 1.7. The kinetic energy per unit weight of the fluid then can be written as alpha v squared over 2g. As for the flux of momentum at the section, it is also expressed in terms of the v, or the velocity, and a correction factor beta. Now, considering an elemental area dA, the flux of momentum in the longitudinal direction can be given as mass over time multiplied by the velocity. Hence, for the total area, the momentum flux is as given in equation 1.8, and through rearrangement, it can be defined as in equation 1.9. This beta here is known as the momentum correction factor and is equal to or greater than unity. So, for the case of a uniform velocity distribution, the coefficients for alpha and beta both have a value of unity. For any other variation, alpha is larger than beta and beta is larger than 1. In this example, the velocity distribution in a rectangular channel of width b and depth of flow y0 was approximated as v equal to k1 square root of y, which k1 is equal to a constant. You are to calculate the average velocity for the cross-section and the correction coefficients alpha and beta. So, since this is a rectangular channel, the area of cross-section is given as A equal to B y0. Then the average velocity is given as you have seen previously in equation 1.3. So from that equation 1.3, we can simplify it to become the V equal to 2 over 3 K1 square root of y0. Then you use equation 1.6 to find the kinetic energy correction factor alpha, which will give you the value of 1.35. And as for the momentum correction factor beta, use equation 1.9. This will give you a value of 1.125. In terms of the discharge Q, we can actually use the continuity equation statement of the law of conservation of matter. Hence, in other words, Q between two sections can be given as V1A1 equal to V2A2. So, for example, given in this figure 1.10 for a partially valid flow, the discharge at any section which is a distance x away from section 1 can be given as in equation 1.35. But if let's say your Q asterisk is equal to a constant, equation 1.35 can be simplified to become Q equal to Q1 plus Q asterisk multiplied by X, which is the distance from section 1. And at Q2 or at section 2, the Q2 is equal to Q1 plus Q asterisk multiplied by the length between the two sections. Let us look at this example. In this example, the velocity distribution in the plane of a vertical sluice gate discharging free is as shown in the figure below. You are to calculate the discharge per unit width of the gate with the information given in the table. The component of velocity normal to the y-axis is calculated as Vn equal to V cos theta. This is considered as average velocity over an elemental height delta y. Then the discharge per unit width is given as Q equal to the summation of Vn multiplied by delta y. This is considering that the velocity is 0 at both the boundaries, that is at point 0 and also 7. So, from the data of the table, Q will be equal to the y, which is the distance from the bottom of the channel, multiplied by the velocity cos of the degree. By doing the summation for each of the element from 1 until 7, this will give you the Q as 0.6897 meter cube per second per meter width. Now we're going to look into the energy equations. For a one-dimensional analysis of steady open channel flow, the energy equation is given in the form of the Bernoulli equations. According to this equation, the total energy at downstream section will differ with the total energy at the upstream section by an amount which is equal to the loss of energy between the two sections. So in the Bernoulli equations, for a section, there will be three components as given in the equations in this slide, where the energy H or the total energy H is given as ZA, which is the elevation head, plus D cos theta, which is the pressure head, plus alpha V squared over 2G, which is the velocity head. So, taking the Bernoulli equation between two sections, namely section 1 and section 2, as shown in figure 1.13, the total energy at section 1 is given as Z1 plus Y1 cos theta plus alpha V1 squared over 2G, while the total energy at section 2 is given as Z2 plus Y2 cos theta plus alpha V2 squared over 2G plus the losses given here as HL. So, having said that, in other words, the total energy at section 1 is given as H1, which is, as I mentioned earlier, Z1 plus Y1 cos theta plus alpha 1 V1 squared over 2G, and the total energy at section 2 is given as H2 equal to Z2 plus Y2 cos theta plus alpha 2 V2 squared over 2G. Now, if the channel slope is very small, this cos theta value will be almost equal to 1, then the normal section is practically the same as the vertical section, and the total energy at any section can be written to be as just Z plus Y plus alpha V squared over 2G. Now, let us take a look at this example. In this example, the width of a horizontal rectangular channel is reduced from 3.5 meter to 2.5 meter, and the channel bed or the flow is raised by 0.25 meter in elevation at section 2. At the upstream section, which is the section 1, the depth of flow is 2 meter and the kinetic energy correction factor alpha is given as 1.15. If there is a drop in the water surface elevation at the contraction and is given as 0.2 meter, you are to calculate the discharge if the first condition, the energy loss is neglected, and the second condition, the energy loss is 1/10 of the upstream velocity head. The kinetic energy correction factor at the contracted section can be assumed as 1. So, to solve this problem, the first thing first is we need to calculate what is the flow depth at section 2. So, if we refer back to the figure 1.14, at section 1 or Y1, the flow depth is 2 meters. So at section 2, basically is 2 meters minus by how much the bed has been raised up, which is 0.25 meter, and minus 0.2 meter, which is the difference in the water surface elevation given in the questions. So the flow depth at section 2, which is Y2, is equal to 1.55 meter. Then by using the continuity equations, where your Q1 is equal to your Q2, or in other words, because your Q is equal to AV, so B1 Y1 V1 is equal to B2 Y2 V2. From this, we can substitute in the value of your Y1 and also your value of your Y2, as well as the width at both of the section. This will give you the relationship between V1 and V2, which is V1 equal to 0.5536 V2. Then we can go to the first condition where there is no energy loss. So if we take the energy equation between section 1 and section 2, we can get the expression of Z1 plus Y1 plus alpha 1 V1 squared over 2G equal to Z1 plus delta Z plus Y2 plus alpha 2 V2 squared over 2G. Given in the question, alpha 1 is 1.15 and alpha 2 is 1. So if we rearrange this energy equation, we will get V2 squared minus 1.15 V1 squared over 2G equal to Y1 minus Y2 minus delta Z. So if we put in the value, then we can get the expression of V2. So from there, if we solve the equation, we'll get V2 is equal to 2.462 meters squared. Hence, the discharge Q will be equal to 2.5 multiplied by 1.55 multiplied by 2.462, which is the V2 that we calculated just now. This will give you 9.54 meter cube per second. As for the second condition, when there is an energy loss, given the question, the energy loss is 1/10 of the velocity head upstream. So HL is equal to 0.1 alpha 1 V1 squared over 2G, which will give you as 0.115 V1 squared over 2G. Then, by applying the energy equations between the two sections, but this time, you need to plus the energy loss or the HL on the right-hand side of the equations. This will give you as Z1 plus Y1 plus alpha 1 V1 squared over 2G equal to Z1 plus delta Z plus Y2 plus alpha 2 V2 squared over 2G plus HL. Then you can rearrange and simplify the equations to get you alpha 2 V2 squared over 2G minus alpha 1 V1 squared over 2G plus HL equal to Y1 minus Y2 minus delta Z. Substituting alpha 2 as 1 and alpha 1 as 1.15 as given in the question, and also HL equal to 0.115 V1 squared over 2G as we have calculated earlier, and also V1 equal to 0.5536 V2 also as we have calculated earlier, then we can get the V2 square over 2G multiplied by 1 minus 0.9 multiplied by 1.15 multiplied by 0.5536 square equal to 0.2. Then from there, we can get V2 as 2.397 meters square. Hence, the discharge Q will be equal to 2.5, which is the width, multiplied by 1.55, which is the flow depth at section 2, then multiply by V2, which is 2.397 meters square. This will give you your Q as 9.289 meter cube per second. That is the end for this lecture. Thank you.